One thing I forgot, sorry. So in the program we had, there's an hour for each speaker, but they only actually have 50 minutes to talk, and then there's 10 minutes for questions. So that could be 10 minutes of awkward silence, or you could make the most of it and ask lots of interesting questions. So if you're a PhD student, there's no such thing as a silly question. Please do ask. But I don't think that's going to be a problem for our next speaker.
Okay. That sounds scary. Thanks indeed. Thanks so much for the kind invitation. Warm welcome, everyone, and thanks to the organizers for all the effort and sweat of setting up this wonderful workshop. Now, unsurprisingly, given the theme of the workshop, this talk will be concerned with quantum algorithms, or, well, rather specifically with one single specific quantum algorithm related to a sampling problem when we have a look at the ever increasingly ironic situation of boson sampling in the light of sampling complexity. Now, I should possibly start the talk with an apology, because earlier in this theme, in fact, at the very beginning, I've already given a talk on boson sampling, and there should be a lot of overlap. I hope the overlap in audience is not too large, but I think this I'm rather on the safe-ish side. But this will be a much extended version, and this will have more of a kind of a quiet and a review flavor, and it will also take into account some interesting recent developments since we first put out our note on boson sampling and sampling complexity. So this is a quantum algorithms workshop, and it's the first talk, so it cannot hurt too much to put up a slide that claims that some quantum algorithms can solve problems in polynomial time on a quantum computer that are thought to be intractable on classical computers. But then we're also rather painfully aware that to actually build such a device in the lab is not such an easy enterprise after all, and the polynomial but huge overhead due to fault tolerance does not particularly help here. To add insult to injury, even disregarding fault tolerance, depending on the specific architecture chosen, the overhead, the additional overhead can be large, or in fact rather daunting in one way or the other. For example, in the linear optical computing mindset, it's kind of this idea of doing quantum computation with single photon sources, then linear optical circuit detectors, classical kind of measurements, and classical post-processing, and having later measurements and operations depending on earlier measurement outcomes. One needs like a constant number, but say 10,000 beam splitters to realize a single C0 gate that operates at the fault tolerant threshold with this kind of KLM type linear optical scheme. To be fair, this overhead can be reduced, in fact, by orders of magnitude by resorting to linear optical measurement-based schemes, but, well, the overhead is still challenging, or in fact rather daunting. So people were thinking, well, wait a minute. Of course it's great to build, or to think of building a universal quantum computer as a physical device in the lab, but maybe it's a good idea as a kind of milestone along the way, as a kind of intermediate step, to just realize something, some quantum device or some quantum algorithm that presumably outperforms classical computers no matter what. Yeah, so that links to this notion of quantum supremacy that John Preskill put out not too long ago, semi-jokingly on his blog, of going into the lab, do something there with present technology that does something for which cannot be classically efficiently simulated, or at least for which there are strong reasons to believe that this could be the case. And a couple of contested candidates of that type of mindset in the literature. One is surely the D-wave machine, and another one is the boson sampling setting that will be in the focus of this talk. And in a way, the boson sampling computer is a linear optical computer of the type that I mentioned earlier, but it's a very simple linear optical computer, at least from an experimental perspective, because there's no conditioning or detection and later conditioning on earlier measurement outcomes, things that are rather beyond current technology anyway, but one just prepares bosons, lets them go through a multiport, and detects them at the end of the day. So, more specifically, the boson sampling problem goes as follows, where one has m modes, m linear harmonic oscillators, m optical modes. One prepares n single photons, so the input state vector in second quantization would be like 1, 1, 1, 1, 0, 0, 0, 0. And then lets these bosons go through the multiport, which means that one linearly transforms one set of bosonic operators unitarily into a new set of bosonic operators. So the entire network is described by a UM element. That's in a way the input to the algorithm. But it should be clear that this unitary is not acting in Hilbert space, but it's transforming modes. So phi of u is the Hilbert space representation, or the metaplectic representation, if you want. And at the end of the day, one measures the photon numbers, one looks at the click pattern, so one gets an output pattern of non-negative integers that sum up to n, the number of photons. So let's do the experiment. Let's have 4 photons coming in. We do the experiment. What we get is, okay, here, do the thought experiment. We get 0, 2, 1, 0, 0, 0, 0, 1. Okay, let's do the experiment again. 1, 1, 0, 0, 0, 1, 1, 0. Well, it's random. That's boson sampling. It's like a quantum version of a golden board where balls kind of fall through. So how can one realize such a linear optical device in the lab with an arbitrary unitary? Well, it's not difficult to see. It's a consequence of the Householder transformation in computer science that an arbitrary unitary can be decomposed into 2 by 2 unitaries of this shape. So of the order m squared beam splitters are enough to realize an arbitrary unitary of that sort. What is the probability of getting a certain outcome? And that's, of course, the entire twist to the problem. So the probability of getting a certain output pattern S, so some word of non-negative integers, summing up to 1, is up to a prefactor which is not so important, just given by the permanent, not the determinant that has minus signs and plus signs, but the permanent with all plus signs of a matrix that's a submatrix of the unitary that describes the network that's obtained by using the first n rows and then as many columns as there are bosons in the specific output word that you have. And that kind of permanent of this submatrix gives rise to the probability of obtaining that specific output word. Okay, well, we also know that to compute the permanent is not so easy. It's a computationally difficult task. Permanent is sharp P hard. So we cannot classically efficiently determine the probability of the respective outcomes. Okay? But then to be fair, in order to classically simulate the device, one does not have to compute all the probabilities, but one only needs to be able to sample from that distribution, which is a different and presumably an easier task after all. But now enters Scott, who says, okay, but the sampling is still an interesting and computationally difficult task. So here's the non-technical way of saying that, but that already captures the essence of the problem, which says that the sampling from a distribution that's close in one norm to the true boson sampling distribution is computationally hard with high probability if the unitary U that describes the network is chosen from the Haar measure and m, the number of modes, increases sufficiently fast with n, the number of photons. Yeah? So a bit of more technical way of saying that is that, well, if one has exact boson sampling, then one would get an immediate collapse of the polynomial hierarchy. But even for approximate boson sampling of the true distribution, a fast classical algorithm would imply a BPP to the power of NP algorithm to approximate the permanent of a matrix with IID normally distributed entries. But this problem is conjectured to be sharply complete in the first place. So in this sense, even approximating the true distribution is supposedly a hard and computationally difficult problem. At this point, I should also maybe advertise a nice paper by Mick and Dan Shepard and Richard Josser that also has a similar mindset, following a similar mindset that's kind of following a similar line, but I'm not going into detail here. So people were kind of digesting this and thinking, wait a minute. So in order to have a device in the lab that presumably outperforms classical computers, that does something interesting, that does something hard, one does not have to kind of think of realizing KLM-type linear optical quantum computational schemes, so things that are out of reach with present technology anyway, or at least for some time. But one only has to send photons through multiports and detect them and sample from them. And that would already be a hard and interesting task in this way. What is more, there was a very exciting experimental development recently of realizing multiports on top of chips in integrated optical devices where modes are like waveguides on top of atomic chips, and beam splitters are realized by bringing waveguides close to each other and letting the evanescent waves overlap and realizing beam splitters in this way. So a number of leading quantum opticians went into the lab and realized this device in a very exciting experimental development. So there were 2 science papers back to back, like this one and this one. There were a Nature Photonics paper, another Nature Photonics paper, and many other papers that were presenting that interesting experimental development, and about 1 million of popular science articles that's covered around that. There was a huge excitement and an explosion of experimental interest. That's all very interesting. At the same time, I hope this seems fair to say, it's also true that the claims made were a little bit grand and loud. People said, now we have devices in the lab that outperform classical computers, and that the extended church Turing thesis is under threat, and like rather kind of rather strong claims. And it will be the point of, it was the point of our original note, and it's the point of the rest of the talk to be a little bit careful here and highlight an aspect that was not sufficiently or not very much appreciated in the first discussions on the subject, which still seem to be key to the problem. So I don't have full answers to this, but I will take a kind of careful attitude, and we will look at a specific problem that was not quite appreciated in first discussions on that, which relates to this innocent question, it was filling up. So how do we know whether we are correct in the first place? So this is not an NP problem. There's not a P witness that we can just check, like in factoring or so. But it's a sampling problem. Experiment samples, you just get lists of numbers, long phone books. So how do we know whether you're correct, and how do you know that the device that you have in the lab is actually the one that you hope to have in the lab, or whether the thing in the lab is doing the right thing after all? And that's the crucial question of certification that will be the topic of the rest of this talk. Now there's a couple of fine prints and flavors in which one can look at this problem. And well, there's different kind of different ways of looking at the problem, and we will go carefully through this list of mindsets, like one by one, and then we will in the end meditate what this all means. So I will surely not use up the hour. There will be some time, and I don't have like strong claims at the end, but I will say what it is, and then you can judge for yourself. Yeah? So in the first part, we will look at symmetric algorithms that in a way look at samples alone, taking the sampling problem as such serious. In the next subject, we will look at a partial validation of the scheme, but only of some features. So it's kind of less and more at the same time, as you will see. Then we look at notions of what one could mean by an efficient classical simulation of the problem, and then turn to boson sampling under errors, and in the end we'll meditate and kind of wrap up to see what this all means in one way or the other. So let's look at our first flavor of certifying black boxes with symmetric algorithms. Okay, so you want to certify the black boxes, the thing that produce lists of random numbers, as a decision problem, and would like to reach a decision from a number of samples of a given order in the natural system size of the sampling problem, which here is the number of photons n. So if, in the good instances, the algorithm decides, accepts with a probability of 2/3 and rejects with a probability of 1/3, we would say it decides the problem. If no such algorithm exists, we would say that it cannot be decided from that order of samples. Now, there's a couple of flavors in which one can look at these raw sampling problems and these sampling complexity questions. The flavor that is specifically interesting here is the one where we have an unknown distribution P, hi Richard, and a known distribution to which we come in a second. And we would like to find out whether we actually sample from P, from the P device, or from Q, just by looking at samples alone. So in this first part, we look at symmetric algorithms that are general algorithms, like as much as you can do, but that only take into account the samples alone. So the unitary is not taken into account, which is a reasonable assumption given that it's sharp P to use the probabilities anyway. But otherwise, it kind of makes all the use of all the information that you can get by looking at the samples alone and kind of ticking how many times a specific outcome has come. So specifically, precisely, these are algorithms that are invariant under permuting of the samples in each sequence of length L and relabeling of the sample space, but otherwise are general algorithms, in this sense, looking at samples alone. So at the beginning of the argument is a variant of the birthday paradox, which is commonly related to the problem of among n different people, that two people have birthday on the same day. And the paradox arising from the observation that this happens rather early on, so the probability is larger than 1/2 with as few as 23 people. So here we need a kind of an anti-birthday paradox in that we ask what the probability is that L samples that are drawn independently from not necessarily identical epsilon flat distributions over a finite sample space are all different, where epsilon flat just means that the highest probability that is occurring at all is epsilon. It's like a min entropy type quantity. And then, maybe unsurprisingly, if the sample is kind of small, then the probability of them all being different is rather high. The second ingredient we need is the concept of a fingerprint matrix, C, that in a way collects all there is to know by looking at samples alone and kind of ticking and looking at the samples. And specifically, this fingerprint matrix C of two samples of length L, this one and that one, is the matrix that's obtained with the entries CAB being the number of elements that appear exactly A times in the first sequence and B times in the second sequence. It's kind of the fingerprint. It says what it is. I mean, it's kind of the essential information about the samples by not looking at the specific labels, but just ticking how many times a specific sample has appeared. Of course, there's also the trivial fingerprint matrix that corresponds to the situation of no sample appearing more than once. Okay. Well, the next step is to see that if you draw samples from either of the boxes, and not too many of them, if you draw L of the order 1 over epsilon to the power of 1/4 many samples, which are drawn from epsilon flat distributions, then the probability of this fingerprint matrix not being the trivial matrix is rather small. It's of the order of the square root of epsilon. And then you can possibly guess how the rest of the argument is continuing. And that will be sketchy now, although this is, of course, the main kind of technical argument that's involved here. It's to show that, in a certain sense, the distribution that you get is very epsilon flat with a very small epsilon with very high, with overwhelming probability. Oh, so this is another, I should emphasize this, that if you take distributions which are epsilon flat, and a symmetric algorithm that takes samples of the black boxes as input, and they are provided not too many samples of the order 1 over epsilon to the 1/4 many samples from each black box, then with the high probability 1 minus order of 1 over square root of epsilon, it outputs a constant value input independent of the inputs. So in other words, few samples from flat distributions are utterly useless, and you look at the samples, you make kind of lists of numbers, you make fingerprint matrices, you make ticks, and if the distribution is too flat, then any symmetric algorithm will just put out some bit that's even uncorrelated with the input. It will be independent of the input, and in this sense, few samples from flat distributions are just useless. Okay, and then the end, as I said, of the argument will be to look at in what sense, with what high probability, the distributions seem to be rather flattish. Yeah, and this I cut short, but it will just give you an impression of the type of argument. I mean, there's a huge tradition in random matrix theory to look at Haar-measure unitaries and showing that submatrices of that unitary look up to a rescaling like Gaussian IID distributed random variable matrices. And so if you evaluate a function of that submatrix, it looks like evaluating a function over Gaussian IID random variables. And here one only needs a specifically tight multiplicative error bound of that type, but it's a kind of a specifically tight flavor of a type of question that has a huge tradition in random matrix theory. And then at the end, one makes use of large deviation bounds to show that if you draw Haar-measure unitaries that are kind of the inputs, then with overwhelming probability, the distribution is very flat. It's exponentially flat with exponential probability if you draw random unitaries. So you go through this argument on the uniform birthday paradoxes, properties of fingerprint matrices, few samples are useless, the flatness of the distribution, and then you end up at the argument that you have here. So you take a deep breath, hyperventilate, and you ask, okay, what does it mean? What it means is you take a Haar-measure random unitary, and then it is, with probability super exponentially close to 1 in n, impossible to decide from polynomial many samples with a symmetric algorithm whether a given black box samples from the actual Boson sampling distribution or from the plain uniform distribution. Yeah, in other words, you go into the lab, somebody has this $1 million device or $2 million, some sophisticated integrated optical circuit device, producing samples from a distribution and getting long lists of numbers. And then a grad student comes in who has a kind of MATLAB on his laptop and programs like within 10 minutes, like 2 lines of MATLAB code that spits out the uniform distribution, and the outcome with symmetric algorithms by looking at the samples alone cannot be distinguished one from the other. Yeah? So in this sense, the Boson sampling distribution is indistinguishable from the uniform distribution. So the lesson is, from sampling alone, not using information about the unitary, one cannot distinguish the device, this kind of $1 million device, from a simple uniform random number generator. And in this sense, it can be classically simulated, or in this precise sense that to the extent it can be verified, it can also be classically efficiently simulated, because, of course, the uniform random number generator can be, well, more than efficiently, actually very simply be generated efficiently, classically. Okay, good. So this is a general argument about sampling complexity. It makes use of kind of interesting tools in their own right, which is not so special about Boson sampling. It does importantly not speak about all polynomial time algorithms, but symmetric algorithms, as we come in a second, but it gives the right intuition to which we come also in a second. So again, in this sense, you have this distribution. You will look at the pattern. Can you just, at the same time, it cannot operationally be distinguished in this precise sense from the plain uniform random number generator. So is the distribution uniform? Well, of course not. Is there structure hidden in the distributions? Well, of course. And it's just very difficult to distinguish that and kind of get the interesting structure out of the distribution. Now, can one discriminate the Boson sampling distribution from the uniform one? Yes, this is correct. And that's already true in the so-called state discrimination setting, where one makes use of a full knowledge of all the relevant probabilities that come out, which, well, takes exponential computational resources, because along the way you solve Sharpie problems to compute the probabilities. But if you do that, then you can use of these nice relative Renyi entropy methods that also Kuhn-Laudenard and Frank put up, and they also talked about that in this scheme, relating to the state discrimination setting with finitely many samples. And then using these techniques, one finds that n to the power of 3 samples are sufficient to discriminate that. So this structure is there, one can discriminate that, but this requires exponential computational resources. So, are there ways out? I'm a bit fast. I have a kind of knob on my talking speed. Am I too fast, too slow? Reasonable? Good. So are there ways out? Well, that depends on what one wants, right? If one is not so much interested in validating the true distribution or finding out what the distribution is in the first place, but if one is only interested in a kind of restricted property of the distribution, or at the end just wants to have an answer to the decision problem of is it uniform or not, then one can go, in fact, much further that we look at in a moment. So that relates to the partial validation of some features of the distribution. So one can efficiently see some signatures of the deviation from the uniform distribution. To start with, the complexity claim is related to the collision-free sector of the distribution, which means that you only look at those outcomes for which there's at most one photon per mode, only the binary words. And that's kind of a 1 over poly subset of all outcomes, as you can easily see. Yeah? But, well, I mean, you make the experiment. Of course, you get more structure. You get 2 photons in some slot, 3 photons, and so on. There's some bunching with some specific pattern. And that pattern of bunching can already be used as an indicator of the deviation from a uniform distribution. That has nothing to do with the hardness claim, but it is what it is. Also, Scott put out a nice estimator, the squared product of row norms estimator, which is constructed by looking at the sums of absolute values squared of a row of the matrices that enter the permanent, and then the products thereof. Some quantity that can be computed in polynomial time, and then one finds that if again the scaling of the number of modes is appropriate with the scaling of the photons in the problem, then one finds a linear time computable estimator such that for sufficiently large n, the photon number, and with high probability, one has that this estimator evaluated over the true Boson sampling distribution, where you draw Haar-measure random unitaries, and look at the quantity, compared to the one where you throw uniform distributions at that. It gives this expression here from which one can discriminate against the uniform distribution, just as an answer to that decision problem. So this was also used just a couple of days ago in experiments in Rome by the Sciarrino group, and also in Bristol in a nice experiment. So using that, one can discriminate against the uniform distribution. Does that say a lot about the distribution? Well, of course not. Do you kind of certify whether the device is doing the right thing, whether it's correctly working. Well, also no, but what one does get is one finds that the machine is doing something that's surely not uniform. That decision problem can be efficiently answered. But again, so does that show kind of this supremacy, quantum supremacy? Well, no, because I mean, one only looks at this specific property, is that uniform or not, and that can be efficiently checked. In fact, for any such test, it's true, and it's kind of a subtle issue, that it's true that, of course, there's another distribution, that a mock-up distribution that gives rise to the same pattern with respect to the test that you are doing in the lab, which can, of course, be perfectly classically efficiently simulatable. Yeah, you look at the test, then you do the test, you find, yeah, it's kind of not uniform or so. At the same time, it is true that there's a mock-up distribution that you again can just quickly and efficiently do classically, that gives rise to the same pattern. So in this sense, you do something in the lab, you have this expensive device, and then you do something else, and but there's again an efficiently preparable distribution that gives the same pattern. So in the end, there's always a classical, efficient story and an efficient explanation for the same pattern what you could have had. But one should not be too negative about things. One can, if one kind of switches minds a little bit, one can see a lot of things, right? I mean, one can efficiently compute, for example, expected photon numbers given the unitary, what the photocurrent would be. I mean, there's a triviality to compute that from the unitaries. One can compute also higher moments thereof. One can compute all kinds of cross-correlators, and even for many modes. That would be inefficient in the number of modes, but one can compute all kinds of properties for a constant number, compute them, and you can also go into the lab, measure them, and get some confidence of whether the experiment in the lab is doing the right thing. And if you always get the right answer, you would get some trust into the device. You would say, yeah, it's interesting, it's doing something right. And this is absolutely possible, and that's a perfectly valid mindset that one can take. One can compute a lot of properties even in an efficient manner. So one can push this even further and ask to what extent these tests give rise to valid answers with high probability if one draws Haar-measure random unitaries as the input to the algorithm. So that's something that we've spent quite some time with in recent days. So one can ask questions of what is the expectation value over Haar measures, the Haar integrals over expressions of the type like kth moments of the photon number distribution at a certain site, which can be expressed in terms of Weingarten functions. So there's a Haar-measure integrals that contain as many U's as U daggers, and there's a nice exercise in representation theory of using the orthogonality relation of irreducible characters and some combinatorial problem to come up with a closed form expression of you draw Haar-measure random unitaries. What's the expected value of getting a certain moment in the photon number that you get out? But you can push that even further and get the full moment generating function of all these moments, which is more than all moments, but from which one can compute all moments in a closed form. And the same can be done also for cross-correlators between different photon numbers. So not only can one for a given unitary compute a lot of things, go to the app, compare things and get confidence whether you're right, but you can also say, am I likely to be right with that? So what is the probability of having a good test over Haar-measure instances that you've drawn and used in the lab? So this is a nice, more sophisticated toolbox of detecting a deviation from the uniform distribution. Indeed, that can be done. But you can also compare that with other distributions that you think you might have had in the lab, and you can again check that, and you can be sure you are right with high probability over Haar-measure random unitaries. Yeah. So, for example, you can ask, okay, I have a device but maybe my photons are not indistinguishable, but distinguishable. That's a common problem in experiments. There's mode matching problems, and you get the nice interference patterns only if all the photons are really indistinguishable. But, well, I mean, how would you know? I mean, there's spatial modes, you bring them together, whatever. And you would not see that in the first moment's picture. I mean, it's like a golden board, the bosons go where they go. But in the correlations, you see a difference whether the bosons are distinguishable or indistinguishable. And that's some pattern. And using that machinery, you would have a nice machinery to detect that from that distribution, and you would be right with high probability. And that would be a nice tool that also relates to work done in Bristol, in the O'Brien group, also with help of Terry Rudolph. So one can see that you can distinguish stuff from interesting distributions, even efficiently, even with high probability, compared to something that you think you might have in the lab. So that's kind of the positive mindset. That's perfectly possible, and that's valid, right? I mean, this is also a reasonable mindset. You go into the lab, you do something, you compute things, you compare, and you will be right with high probability. This is correct, and this is an important thing to know. Does that show supremacy? No. Well, I mean, yes, no, not really, because of course you get a pattern, you can get trust of a certain type, but you can always find again a classical machine, a classical device that would have given rise to the same pattern, to the same distribution, to the same sophisticated cross correlations that you've cooked up. Again, you can find a classical explanation, a classical machine that would have given rise to the same pattern. This is not a contradiction. This is kind of the ironic situation that all these statements are mutually true at the same time. It's not contradicting. They're only kind of morally contradicting somehow. But it's perfectly possible to compute these things, to compare. At the same time, it's true that you do all this sophisticated stuff, but there could have been a classically, efficiently sampleable explanation of the same thing with no quantum device whatsoever. Yeah? So, which brings me to I'm a bit fast even. Okay, I'm so excited about it. The efficient classical simulation part of things. So what is this? So what about these mock-up distributions, these classical explanations of the same patterns? You have a distribution, you get some pattern, you have some indicator, some estimator, you get a pattern, you want to learn something. So how about these classical, efficiently preparable explanations of the same things? Now there's a nice find, literature find by Fernando Bradau that relates to that has quite funny implications in this sense. And this is what it says. I read this statement here. So D is any distribution over was just a binary word, over binary words, such that the min entropy is large. Well, that's essentially the flatness earlier. Well, min entropy is just the same thing up to a logarithmic rescaling. Then, for every t, every circuit t, and any epsilon, there exists a circuit of size, what it is, a bit larger, but not too much larger, that samples a distribution d prime that has also a large min entropy, but which is epsilon indistinguishable from d by circuits of its size at most t. Okay? So, this is a statement. So Fernando looked at that and the kind of, well, I mean, it's kind of rather clear how to apply that to the Boson sampling distribution that gives rise to the following statement, that again, you take m, the number of folds, large enough, in the same setting as throughout the talk. And then you draw Haar measure random unitaries. And then one finds that with probability of at least 1 minus delta, and every t and every epsilon, there exists a circuit of size, well, a bit larger, but still polynomial, that samples a distribution that's epsilon indistinguishable from the collision-free part of the Boson sampling distribution, the true quantum Boson sampling distribution, by circuits of size at most t. Yeah? And again, collision-free part of, that's not not a restriction of triviality, because all these claims are always within the collision-free part of the thing. So if you think of it, so you have a circuit T, and then you can always find a class of circuits of size a bit larger, that sample distribution, but perfectly classically efficiently, that is not distinguishable from the output distribution of the Boson sample. It's a bit like a race. It's like a hierarchy. So the thing is, there is a universal, classically efficiently preparable cheating strategy that fools all short verifiers, like short circuit verifiers, but that's true for all settings, for all k. So you can look at kind of hierarchies of preparable circuits and tests, and you can never outperform that. So forever, you can always cheat. And there's always, in this sense, a classically efficient explanation for what you get. And if you're unhappy about it, then make the circuit a bit longer, and you would still end up in the situation that there is an efficiently preparable cheating strategy that fool the short verifier, and if the verifier are a bit stronger, then you find another circuit that does something classically efficiently that you cannot distinguish from the true Boson sample distribution. Yeah? So again, you are in the situation that you go into the lab, you have some device, you think you have some intricate strategy, and it's absolutely true. You can compute lots of properties like densities, correlators, and interesting features, and you can develop trust that your machine is doing the right thing, and that's a valid picture, and maybe that's all there is to say. I mean, I can be perfectly happy with that and then say, okay, I have a device, it does something, it does what it does. But at the same time, I should be aware that it's not a contradiction, that the very ironic statement is true that no matter what you do, no matter how intricate your algorithm is, there's always a kind of cheating way of having a perfectly classically efficiently preparable explanation for the same thing. And in this sense, it's unbeatable, because if you say, I get more sophisticated, but there's another strategy that does it, and so on. So in this sense, and that's not a contradiction mathematically. It's just morally a bit weird, but it's true at the same time that there could have been maybe a more intricate story, but a classically efficiently preparable intricate story of the same thing. Yeah? And this is all true at the same time. Okay, final step, and we promise to be very nicely within the 50 minutes. So that's just one slide. Boson sampling under errors. Of course, if you want to classically simulate the device that you have in the lab, you don't have to simulate the perfect Boson sampling device, because life's tough. There is no perfect Boson sampler as a device. Every real experiment will have errors. It will not be perfect. And there's a nice work on identifying what type of errors one has by Peter Rodi, and there's work by Raoul on the necessity of fault tolerance in the presence of errors, and so on. So the question is, does the problem become harder if you want to simulate a faulty device, or easier? I don't know. It's unclear, right? But that's an interesting question. What I do know, although, is that in the presence of very large errors, you can do it. In fact, you can, in a very strong sense, simulate the device. So for constant errors, so all these devices have some constant faultiness, so that doesn't scale up, but it's rather bad. So it's so bad that all the sources and each Minkowski isomorph of all the gates and so on, they all have positive Wigner functions. Yeah, but then one can efficiently just sample the entire circuit up to a constant number in one norm for fixed faulty devices. Yeah? So if this is the case, then you can really, even in a stronger sense than before, really just sample out the full thing with a constant error in one norm. So in this sense, it becomes easier if you are very noisy. Yeah? What does it mean about the intermediate bit? Nothing. But it poses an interesting question, like where's the boundary? How far can you go to still be able to efficiently classically simulate things in this strong sense? In one norm, I don't know, but it was an interesting open question to look at. Which brings me kind of to the blah blah section of the talk, the outlook and summary. What does this all mean? I don't know. Judge for yourself. I mean, what's the point of boson sampling? I mean, the boson sampling problem is not really solving a problem, right? It's not a factoring problem where you know why you want to do it, specifically in these days. But it just, I mean, the main purpose of it was really just to have something interesting, something hard, no matter what. It's not solving a problem. It's just a machine of which you want to know that you cannot classically simulate it. That's the entire purpose of it. And that's a perfectly valid and interesting purpose. As a kind of intermediate step, you want to have something in the lab that for which you think you cannot do it. Of course, that's an important milestone along the way. So the motivation for that is to kind of think in these notions of quantum supremacy. It's a bit of an evil word, maybe one should not use it. And, well, you know what I mean. To have something in the lab that does something interesting and not classically efficiently preparable, and even hope to get some experimental evidence against the extended Church-Turing thesis, that's also often stated, meaning that every process can be efficiently or can be simulated on a classical computer with polynomial overhead. And one would like to gather some experimental evidence that this could be the case without having to build up a Shor-class universal computer, which is not quite around the corner technologically. So does it show it? I don't know. So it may be true, I mean, under the complexity theoretic assumptions, on the hardness of permanent sampling. It's a hard problem to approximate the output distribution, but at the same time, it is true that everything you do, you can also classically do efficiently. So in this sense, you can kind of classically efficiently simulate the device, because for every question you ask, you can find a classically efficiently preparable explanation of the same thing. And there's kind of an unbeatable setting that, well, there might be some structure there, but you can always find a classical explanation for the same thing. Yeah? You can truly certify small-scale instances. That's a perfectly valid point. You make a small device, you make one photon. Well, that's not very interesting. Maybe a one beam splitter, 2 photons. You check. You make 3 modes, 4 modes, and you can check, and you get some trust to the device. At some point, I say, I have trust, I can build my devices. Now I have done a device, I cannot check it, but presumably it's doing something interesting. And that's a perfectly valid standpoint. I'm not criticizing that whatsoever. Fine. But one should be aware that at the same time it's true that one can classically efficiently simulate a device in the sense that there could have been a classical explanation for the same thing. I'm repeating myself, but it's just I only have one point in the talk, right? So it doesn't hurt to iterate a little bit. So indeed, this is the case. So that poses actually an interesting question about what it actually means to simulate something, right? I mean, I don't want to make loud claims here because I don't really know, but I would argue that to simulate something, A simulates B, I would say, if B cannot be operationally distinguished from A. So if there's an object here in the room that looks like a cup of coffee, it smells like a cup of coffee, I drink it, it's good, it tastes like a cup of coffee, I look at it, the shining, in probably every respect I can think of, or actually every respect I can possibly provably do, it is like a cup of coffee, then, I mean, it is a kind of cup of coffee. Or at least I have simulated the cup of coffee. It's a bit of the ontological question whether it is coffee or not is a bit of a metaphysical question, right? I would leave that out, but it's surely a fair thing to say that if there's no operational way of distinguishing the guy from a cup of coffee, then I've simulated a cup of coffee, right? Well, also, I would be happy about it if the smell is right and the taste is right. So, what does it mean to classically simulate a device? Well, I would say this is what it means, and in this sense, one can simulate boson sampling, that in no matter way you think you test a certain property, you could have had a classical efficient description of the same thing, and hence you can simulate it. Why? This is not a contradiction of it being hard and you not being able to really get the right distribution right. But, well, this is the irony of the situation, that to approximate a distribution to a constant error in one norm is not the same thing as being able to efficiently test the property and having a classical explanation for the same thing. Of course, there's still the way out, which is open, that there might be other ways out. which are cleaner and easier. For example, one could look at k-designs, which are kind of random unitaries, which are not so random, but maybe they're random enough to show the hardness claims, but at the same time they're not so random that you could still see features in the distribution and can nicely distinguish that. That's a perfect option, nice research topic on random circuits, k-designs, and so on, but this is an open question. What one can also do is one can kind of see or think of partial certification. One can rip off the sources, rip off the detectors, and just say, I want to certify the middle part and check whether this is right. And there seems to be good indications, this is work in progress, that by using coherent inputs and doing the right sampling, a bit compressed sensing like, one can get an estimate with the one-to-one norm closeness to the anticipated channel with high probability, which works much cheaper than full process tomography, but it's still inefficient in the number of modes. But for small system size, one can do it. So one could kind of certify the circuit that it's right, and then one would again put the sources there and the detectors and sample, and then again it would kind of look as if you could have classically simulated it in the way that we looked at before. So what does it all mean? I don't know. Okay. We looked at linear optical quantum computing. Then we highlighted the specific problem of boson sampling as a device that's presumably doing something in the lab that you cannot do classically efficiently on a classical computer. While this may be perfectly true, we found that the outputs are totally indistinguishable from the uniform distribution with symmetric algorithms. This does not prevent us from being able to classically, efficiently certifying some properties. In fact, a lot of quantities, a huge number of quantities you can check, and we elaborated on tools of finding sophisticated tools that even probably work with high probability over Harman random unitaries. That's a nice representation theory thing. You can do it, you can check, you can get trust, and you know that you are successful with high probability. At the same time, again, there's mock-ups, there's classic explanations. So you can find efficient mock-up distributions. Whatever you do, there is a classical description of the same thing. So in this sense, you can classically efficiently simulate boson sampling. And there might be other ways of certifying, but, well, that's open. As such, as a classical problem, boson sampling in the precise sense, as I looked at, can be classically simulated. But I would rather end the talk with some higher authority than myself, than with this gentleman here, stating that over here we have our random number generator, which says 9999999. Are you sure that's random? Well, that's the problem with randomness. You can never be sure. Thanks so much for your attention.
Okay, great. Thanks, Jens. So, any questions?
Yeah. So I didn't get your last slide on the certification with coherent inputs. What it is about? So you want to know the unitary?
I mean, the boson sampling problem as such is a kind of a classical sampling problem. You have output, you get a list of numbers, it's perfectly classical. You can say, okay, I just want to look at the intermediate part, the channel, the circuit, and I want to know whether my circuit is doing the right thing, trusting the other parts. So you would have a channel, T, and you want to know, is the channel that you have in the lab the one that you think you have in the lab? And then the good figure of merit would be the one-to-one norm, and you ask, can you check by putting right inputs in, feasible ones in the experiment, like homodyning or so, coherent states, and you homodyne at the end, can I get it estimates with high probability that the channel I have is similar to the one that I think I have?
This is what they are already doing in the experiment, right? They are checking what is the unitary they have to do.
Yeah, well, this is kind of a pedantic way of doing it. Of course, this is just like you get a norm estimate and so on. But of course, in any experiment, you do it. Also, what I said earlier, of the type that you look at photocurrents, that's of that type. I mean, you get something and you check, is it right? That's exactly of that type. It's just like even in this strong sense, you can still do it, but it's not efficient. Yeah, and there's good reasons to believe that this cannot be efficient.
What is not efficient?
Oh, I mean
They are doing it now?
No. Look, looking at patterns, that's efficient. Like whatever. I mean, you look at photocurrents and so on, that's efficient. And you could do that for any K modes. Yeah. But then if you ask, I want to have the full channel as a kind of norm estimate for the entire process, and you ask, how does that scale in the number of photons? This is not efficient. But this is, of course, much to ask for. I mean, maybe you want less, just want to know certain patterns, certain features. This is perfectly classically.
And you mean the unitary and the kilo space?
Yeah, well, that's the point. You don't know whether it's unitary. It's just something, right? I mean, you think you know what you have. It should be unitary, but it is what it is. Yeah. Yeah. Totally. Oh.
Okay, so I mean, you know even better than me that there's this massive debate about the argument between you and Scott about this.
Yeah.
But I want to pick up just one thing that I haven't seen in this debate, which you emphasized quite a lot in your talk, about the fact that there's a universal classical mock-up for the distribution. So this is certainly true. So let me tell you a story which illustrates why I don't find this argument at all compelling as a problem. So there's a scientist that's taking some data and observations, and he gets some data and he comes up with a nice model for the system.
Okay.
And then he takes some more data and gets more accurate. He does more effort on measuring his data, and he finds his model doesn't agree with this anymore. But he finds he can make a more complicated model that describes his data, and he's happy again. And this process goes on and becomes more and more complicated. His model, each time he does some more experiments, he finds a more complicated model that's still a mock-up, but still this.
Indeed, we published papers on that,
Indeed.
right?
And I wasn't going to refer to that. So this story is exactly the story that you're telling, and saying that every time you make these observations, you can find a model that an efficient circuit that will generate the samples. But the story I'm talking about is not about algorithms. It's about Ptolemy and Copernicus. Because it's perfectly feasible to keep generating a more complicated set of epicycles.
Yeah.
That even today we could have an epicycle model of the universe, of the solar system. Now, why don't we believe that model? We don't believe it because, each time you took better data, you had to make your model more complicated.
Yes.
And at some point, we come on, this Copernican sun at the center model is much more simpler.
I agree. Indeed,
and this is exactly what's happening in here. At some point, this classical mock-up is getting so complicated. Come on, the quantum explanation is now. We're pretty damn sure it's right. And this is science, not mathematics. And we need to remember that this is a scientific question, not a mathematical question.
Yeah, indeed. I couldn't agree more. Absolutely. I mean, this is what I said. It's all true at the same time. So when I say there's a classical efficient explanation, that's perfectly true. Then, of course, it's also true.
Completely irrelevant. Another example, more in this context, is the fact that if I have any algorithm which I try for some finite number of inputs and I get the outputs, I can always construct, and this could be an algorithm that is factoring efficiently.
Yeah.
Well, I can, or factoring very fast, let's say. Well, I can always construct a mock-up that reproduces that with a log n depth circuit.
Yes.
Which is I just construct the circuit that does the lookup table that produces the right outputs for the given input. So post hoc, after I've seen what I've seen, I can always say, there's a classical story for this that's efficient. You can run this argument for the halting problem. I can have a God machine that outputs the answer to the halting problem.
Well, for finite instance thereof, of course.
And so again, I mean, the fact that there exists a classical story has nothing to do with whether we believe this device is doing something quantum or not.
Well.
It's true for every single experiment ever done, every algorithm ever written, every quantum algorithm ever devised. You can always come up with an efficient classical story. It's just a lookup table.
Well, yeah, this is true, but okay. The thing is, I mean, this is not an NP problem. There's no witness to check and so on. So it is true at the same time as I say that there's this classic explanation, but it's also true, as you say, that the more intricate the experiment becomes, the more intricate your classical explanation also becomes. You would scale that up in a way, and this is also true at the same time, right? The thing is that, I mean, it depends a little bit on what one wants. These are all kind of true at the same time. I mean, if you have a kind of quantum algorithm that does something like that solves the NP problem, sure, then that's what it is. If you have a quantum simulation, I mean, myself, I went on stage and talked about like hardness of looking at Boson-Hubbard dynamics in the log times and so on. And this is in a way of the same type, right? That you get evidence that your machine is right, and then to some extent you trust that you have the right thing, and then you continue. But of course, again, you could have had a classical efficient description of the same thing, so the same argument applies, right? I mean, the thing is, I would just be a bit...
This is a vacuous that this is an empty statement, because this is always true of absolutely anything you ever do in the laboratory. And this is not how we do science. This is not how we convince ourselves that that quantum mechanics is true. We don't...
Yeah, but if the entire purpose of the machine is... I mean, the purpose of boson sum is just that you do something in the lab of which you want to be sure that you could not have done it classically. Then I would just set higher standards and would say, okay, then... I mean, that's what I meant. I mean, I have no conclusion. It's just what it is, right? I mean, I'm not making loud claims or so. I mean, I just say, this is what it is, and then we meditate about this. I'm not saying... Well, I mean, yeah, but since the entire purpose of boson sum is just to do something that is not efficiently preparable, then that sets rather high standards. And of course, one should let all the fine prints in which one can think in what way one can think of a classical simulation, which does not mean that it's not a valid enterprise. You're also right, yeah. But I mean, I think I agree, yeah, yeah.
Maybe it's worth remembering a little bit of the history of the context of this. I mean, also Scott's boson sampling didn't come from nowhere, right? So one of the, I mean, that's kind of more towards Toby. I guess it's true that we don't use an algorithmic test to do science, but it was actually proposed as a test of quantum mechanics if we could build a quantum computer and factor random RSA challenges. This would be a very good case in favor of quantum
But
mechanics.
NP problems are very special because by definition
exactly,
you can verify efficiency.
Indeed, but that's maybe a lesson to learn from that.
So one of the purposes of Scott and also of Nick's, Dan's and Richard's program was to find exactly things that are outside of the hierarchy.
Yeah.
And in fact, even the certification issue arises in any computational problem there, right? So it's kind of business. You presented it as a story.
Oh yeah. Oh yeah.
I mean, this is a fundamental question. I mean, if I claim to be an oracle for a problem in the second level or in p-space, you will have the same discourse how impossible it is to check that, and that you won't believe me ever. But that's not. That's only because your tests are restricted, unfortunately. Because you don't allow, you only want polynomial time classical tests, right? I mean, your world will already change if you have quantum tests. And so...
actually, that's open. In fact, I don't know. That's an interesting question. There might be quantum tests that show it, but this is not known.
The thing is, I mean, I guess we shouldn't be surprised that things outside NP will not serve as tests of the underlying computational model.
I agree, but maybe that's the lesson to learn. That I mean, NP problems have certain nice features, and if you look at sample problems of that type, then that's what you get, and then you can either be happy or not. It's a bit of a matter of taste. I mean, yeah. But there's also positive.
I think it's more than that, because even if you build a real quantum computer, not just a boson something thing, you might maybe want to use it to calculate some ground state energy or energy gaps. And it's not a matter of taste, because we'll have to believe it that it's true. Because we might not have a classical efficient way of...
Oh, totally. No, but that's what I said to Toby. I mean, as I said, I mean, as you know, I mean, I also work on many problems. Of course, if you have a problem to be solved, then of course you would, if you want to look at ground state features, then of course at some point you would have to have some trust on that the device that you have in the lab is doing what you think you're having, and there can be no ultimate kind of verifier that you really have that, because, well, you cannot have that. But then you're solving a kind of a hard problem that's kind of related to a physics question at hand, and then of course you get what you get, and of course you would have some trust in what you have. But here, I mean, the whole point is that you want to have a device that's not classically efficiently simulatable, hence,
You just have to believe it. You have to make sure that the device actually behaves as by prescription, and then you take it.
No, I agree. But then
it's just
I agree.
You personally don't care about the answer, whereas for some grounds that you do.
Exactly.
This is a very personal thing. I mean, this is there's nothing special about it.
I'm not sure. But I'm not sure I agree, because I mean, it doesn't solve a problem. You don't care about the answer, but you just want to know is there a classical efficient description or not? And it is, and not in the sense that we discussed. I mean, that's exactly the point of the discussion. These things are all valid at the same time, and it is what it is. But having said that, I mean, there's also a positive lesson to learn, like in the sense of sampling problems. Like if you look at, like in your style, a question of equilibration, thermalization, and so on. When one talked about like closeness of one norm estimates to equilibrated states and so on. In the end, one should formulate these questions as sampling problems. You make measurements, you sample, what can you learn from a given sample, and what can you infer? So that's a positive lesson to learn from all that. But yes, I agree. I mean, these are all true at the same time, right? These are not contradictions. So that's kind of part of the point, to see that these statements are mutually compatible. And
so I think there was maybe one more question.
I mean,
yeah,
I had a question, but Andreas kind of raised the point.
Okay.
But I think more the point Andreas is trying to say is that computing devices are consistent. So it's not just that you want to solve the Boson sampling problem. You want to be able to build a device that can solve many problems. And this is just an example of an algorithm where you can prove that there's going to be a complexity difference. So, well, you're talking about the fact that you can have you can reconstruct the classical probability distribution that will efficiently, be close.
yeah,
For that given instance of the sampling problem.
yes,
You could also have fed something else into the computer that you built,
yeah,
and you need to have your classical circuit be able to reproduce all such possibilities. And
yeah. But that you mean that you would. I mean, you would have. I mean, that the classic explanation would be. I mean, there would be perfect compatible with all those. That's perfectly fine. Except that for a more elaborate setting, I mean, that's not quite right in the sense that it would generate all the outputs, all for these inputs in an efficient way. Except it's still true what Toby says, that the more sophisticated your type of question becomes, the more elaborate your explanation becomes. This is all true at the same time. So, yeah. I mean...
Okay, great. So
think,
thanks, Jens, again.
Thanks.